All right. Hello, those who are watching online. I've already said hello to people who are here. I'm David. I'm the coordinator of the Maths Learning Centre here at the Uni of Adelaide. It's semester 1, 2022, and this is the revision seminar for Intro to Financial Maths. And I've been given some requests, and I'm going to talk about those things. But what I want to say to you guys is that this is your revision seminar. So if you think of something to ask, when I ask it later on, then bring it up. And feel free to interrupt me if what I say doesn't make sense. Maybe wait till I finish the sentence, but it's okay to interrupt. And it's also okay to interrupt me in the middle of a sentence if I do something ridiculous like 1 + 1 = 1. Okay, so if I make an arithmetic mistake like that and you notice it, don't wait, just tell me now. But otherwise, feel free to interrupt. I'm going to try to remember to stop every 5 to 10 minutes, so just stop talking for 30 seconds so you can process anything. Yeah, but it's your seminar. You get to choose how it goes. So let me know anytime, anything you want to talk about. Okay. So I've been asked over email to talk about basically, well, they say quadratic functions in particular, but anything to do with graphing functions, that's what I've been asked about. So I thought I'd start there and then we can move on to anything else afterwards. If I have it right, this is the course where half of it is called algebra and the other half is called functions and annuities, I believe. Cool. All right. So this might be a bit different to the way the lecturer does it, but that's the point of a revision seminar, to possibly be a little different. If anything is wildly different, do let me know. Right. Function is a big idea in maths. It was an invention of mathematics, of mathematicians long before any of the notation that we have to talk about functions arrived at, like before they used X, like that, but they didn't call them functions till a lot later. And the idea of a function is that there's a general idea of function, and then there's a one specifically for numbers. And the idea is that you put a number in, and then you get a number out. That's what a function is. Technically, you can define a function to have any kind of object in, and it spits something out. So classic function would be put a word in and the first letter spits out. That's a perfectly good function. But with numbers, usually you put a number in and then it crunches through some sort of formula and it spits out a number outside. And so usually this is a formula. But it doesn't have to be a formula. It can just be any description you like, as long as formula, this thing, or any description really, as long as when you put the same number in, you always get the same number out. So if you put 3 into the formula, you're always supposed to get the same answer every time you put 3 in. So it's not like rolling dice where you can, where you get random numbers out. That's a whole other thing, which you learn in statistics courses. But in mathematics, a function, as long as there's only for each input. It is possible for different numbers to produce the same output, that's okay. But just as long as every time you put a particular number in, you always get the same answer, then it's a function. Okay, cool. So usually we do functions on numbers, and every number has an answer that comes out. So I could, for example, draw a number line. And then I could say, well, this 0 is going to produce the number 3, and this is going to produce the number 7, and this is going to produce the number 11, and this one's going to produce the number 15. Anyone guessing what the next one's going to be? Got a guess? Good guess. Okay, and so on. And since we're full on in maths, we could technically put one halfway between these if we wanted and do it at a half, and it should produce 5, I guess. So that list of all of the outcomes for all of the inputs, that's what the function is to a mathematician. And you can draw it as a table if you like. I could say, you know, these are the x's, and the x's I've written in my table are 0, 0, a half, 1, 2, 3, and 4. And these are the answers that are attached to each of those x's. And the name of this thing is f. If the you can call the function whatever you want. Traditionally, you call it f. You have a single letter name for your function normally, but there are lots of functions that have multi-letter names. But traditionally it's f or g, because f for function. We're not that creative in maths most of the time, but you can have other names for the function. And so if this thing was called f, then the number that 0 produces is called f of 0. And in our today, our number for that is 3. And f of a half is 5. And f of 1 is 7, and so on. And so what you'd normally see in a table is not this, but f of x. And you'd have 3, 5, 7. So you'd normally see a table without that middle row like that. And this is saying that when I write the symbol, I'm just going to remove that bit, that this number, a name for this number is f of 0. And a name for this number is f of a half. And a name for this number is f of 1. Okay, how are you feeling? Cool, sweet. Okay, great. And this allows us, like, if I've told you what f does, if I've told you what f does, then I'm allowed to write things like this. This can now stand for, you know, I can say things like f of 0 plus 4 is f of 1, for example, because f of 0 is really the number 3 and f of 1 is really the number 7, and so you've added 4. And that's what you noticed, right? That each one was 4 more than the one before it. Okay, not that they always follow those patterns. Right, cool, cool, cool. But it's much more common rather than a table, though a table is a perfectly good way of doing it. Any description that you like, as long as there's only one answer for each input, is a perfectly good way of describing a function. And it's okay for some functions to only take in whole numbers and only spit out whole numbers, or to take in whole numbers and spit out ridiculous decimals. But most functions in mathematics are technically possible to use any number you like, as in no matter how many decimal places they've got. And you normally do that with a formula. This function's formula, I'll put it on the same page, f of x is 3 plus 4x. And that's saying that when I want to calculate what f of 0 is, I can say f of 0 is 3 plus 4 times 0, and that gives me the answer 3, which is the correct answer. And f of 1 is 3 plus 4 times 1, which is 3 plus 4, which is 7, which gives me the correct answer. And so in order to use the formula, then you can replace the number x with whatever number you're thinking of, and that'll create the answer to the formula. Okay, cool. And that's the most common way of describing a function in mathematics, is via a formula. Okay, next stage. So when I saw this number line, you can, and there was a number attached to each of these numbers. I had the number 3 attached to this one. F of 0 was 3, and f of 1 was 7, sorry, and f of 2 was 11, and so on. What we normally do is that you could imagine it as each number having another number attached to it. And it's like an advent calendar at Christmas. When you open the thing, there's chocolate behind it. You open a little window here at number 3 and the number 11 is behind it, which is much less exciting than the chocolate, but we're okay. What we normally do is imagine, instead of seeing it as something that we have to wait to figure out what the answer is, we try and draw a graph of all the answers simultaneously. And so we look at this number here and we go, all right, I can imagine 3 as this height and 7 as this height and 11 as, well, we ran out of space, this height, and so on. I should have drawn a smaller graph, just a second. So 3 as this height, 7 was this height, 11 was this height, and so on. And I can imagine that at a half it was 5, and I can imagine them all as heights. And if the answers were negative numbers, I would have to imagine them as depths that go downwards. And that's lovely, but sometimes a bit confusing. And so we imagine that actually this dot at the end of the line there, we're going to draw it on a grid so that we can see how far up it is. Because I can't see from looking at it that this is really 3. So I draw a nice grid and we go, aha, that's 3 this way. That looks like 4, but it's 3. And then the next one is 5, and the next one is 7. And so that you can see how they look lining up with a ruler on the side. But we could actually treat them as a ruler at every one if we wanted, but that's how the graph is created. And so when you draw a graph of a function from a table, what you normally do is you draw the grid first. I'm doing this because I was specifically asked to make sense of graphs, so I'm being very careful about it. So I know that when the input was 0, that's 0 there, then the output was 3, so I go up 3, and that's where I draw a dot. When the input was 1, the output was 7, and so I go up 7, and that's where I draw a dot. And when the input was 2, the output was 11, so I go up 11, and that's where I draw a dot. And that's how you make a graph 1 point at a time, which is lovely, but one of the vibes of mathematics is to not have to ever do that. Because we've been looking at functions as a worldwide community for, you know, several thousand years and several hundred years after we've made this graph idea. So we've been making the connection between formulas and graphs for a long time, and we know a lot as a community about how graphs are, the shape of the drawing is related to the formula that we write. And so we can fill in the gaps in between and fill in all the gaps in between. And when you fill in all the gaps, you get a lovely straight line from what I've got here. And this is called a graph, or graph if you like. Okay, cool. Right. So I have one last thing to say. So this idea of drawing a height for each number or a depth for a negative number is a great idea, but simultaneously when people were starting to think about that, other people were thinking about this grid all by itself without thinking about it as functions. They were starting to think, well, what if I had a grid and I just drew a shape, right? Is it possible to figure out a rule, a maths calculation rule, that decides whether a dot is colored in or not? That's a different question that we're asking. So this one is giving us a rule for specifically coloring in each dot, 1 X and Y at a time. But what if I wanted instead of having a way of creating this one dot at a time, what if I had a rule that if you gave me the coordinates of a point So for example, this would be the point 1, 1. If you gave me the coordinates of a point, I could put it into some sort of formula and it would tell me whether that point was part of the drawing or not. The point being that I don't want to have to draw the drawing necessarily. I want to be able to tell from the calculation whether it's there. And this is how an online or a calculator, graphing calculator works. It literally creates the formula 1 point. It tests every point and decides whether it's part of the drawing. So that's the other thing you can do. You can have a formula that tells you whether a point is part of the curve or not. And this one, for example, is probably, very careful, something like x squared plus x minus 3.5 squared plus y minus 2.5 squared equals 1.7 squared. So this formula, it's not a formula at all, it's an equation. I can tell whether a point is on this curve if when I put the x coordinate and the y coordinate into this formula, it comes out to the same answer as 1.7 squared. And if it doesn't come out to the same answer as that, it's not part of the curve. Okay, so that's a really complicated one, which is not in this course. But I just wanted to point out that there's two things going on here. And so this is saying that I can locate every point by making an x coordinate and a y coordinate. And then I can decide whether a particular point is part of a particular drawing by subbing the coordinates into an equation to see if it comes out to the right answer. And both of these things are going on when we draw the graph of a function. This one, the x and y, is about locating a specific point. This one, we don't officially have a y here yet. When we first started, there wasn't a line, a grid here. It was just some heights. And so we just drew the heights we wanted. But if you want to locate this point on a grid, suddenly you need a y coordinate. And so that's why people say something like y equals f of x. This is matching with this picture, that the y coordinate of a point on the graph is found by doing f on the x coordinate. That's what that means. All right. So let's say like several hundred years of mathematical development, and it took people a long time to figure that stuff out and feel comfortable with it. Yeah. Okay. So before I stop for 30 seconds and collect my thoughts, if you have anything to say, please do for us. Just saying, people in the Zoom, feel free to chuck things in the chat. I will see it eventually. And in fact, also, people who are in the room, if something appears in the chat, let me know, because I might not see it myself. Okay, so the kind of graph that I drew earlier was a straight line. And it turns out that certain kinds of formulas for functions always produce straight lines. And they call them linear functions, because linear means to do with straight lines. And so this is a linear function because when I draw its graph, it's a line. That's this linear. Okay? And people have been studying these for a long time, and they discovered that you could tell just by looking at this formula where and how steep this line is going to be without having to actually plot any of the points. I can imagine what this line must look like just from the way that this formula is arranged. Okay. But I will also say to you that this is a function way of writing this line. But if I wanted to just write an equation that would check whether a point was on this drawing, I could draw many different equations. So I could write, say, so this is the graph of a function, but I could also imagine that it has a y-axis and an x-coordinate, and there's just a collection of points, and I would have, you know, y minus 3x equals 4 or something like that. Would be a perfectly appropriate equation for this line, but this is a way of writing it as a function. So technically that's the function, and the graph is y equals f of x. And so if you have an equation, so this checks if a point is on the line, but I could do algebra to rearrange it into a function version. So I could say, well, you know, y, it must be 4 plus 3x, and yay, now it's a function, and define the function to be 4 plus 3x, and then it's done. So that's a classic thing. If you have, for whatever reason, you've created a formula, an equation that checks if points are on the graph, that isn't written as a function, it's just got x's and y's everywhere. If you can rearrange it to y equals, then it can be without any y's on, just y equals anything just with x's, then you can call the other bit a function if you want. Okay, cool. And we can discover that the numbers in these positions can tell you the shape of the graph. This one is the y-intercept, which is the place where it crosses the y-axis. And this thing is the slope. Some people call it the gradient. And it doesn't matter which way around we write these. As I said, it's the number attached to the x that is the slope or the gradient, and the number that's not is the y-intercept. And this is specific to this kind of graph, this kind of formula. Different formulas have different interpretations. But for this kind of formula, we can interpret it that way. So when I see something like this, this tells me that it starts at 7, and for every 1 across, it will go down 8. That's the slope. Because it's a minus 8 that's attached to the x. You need to include this minus here. And so if I go across 1, it will have to go down 8, and so it'll go down to here. And if I go across another 1, it will go down another 8, and we'll go down to here. And so you'll get this like that. And the reason it works that way is, well, if I start with x being 0, the answer comes out to 7. If x is 1, I get 7 minus 8 lots of 1, and so I get there. With 2, I'll get 7 minus 2 lots of minus 8, so we go down 2 lots of minus 8. And so this is also a description of how to locate every point on the graph by starting at this point and then traveling up or down based on how far this says. And so that's one way of creating the equation of a line by doing that. You can say, if I had like a random line, something like that, that's a 3 and a 5. So I had a random line like that. I could say, just a second, I know that the y-intercept is 3. And I know that when it goes across 5, it goes down 3. So that means if it only went across 1, that would be cutting this into 5 pieces. I'd have to cut this into 5 pieces as well. But when across 1, it would go down 3 divided by 5. So the slope minus 3 divided by 5. So most people call this the rise and this the run, because people like alliteration, rise over run. But you can think about it as, well, I know how quickly it goes across for 5, it goes down 3. So I know how quickly it goes down to 5. So I have to cut this into 5 pieces to know how far it goes for 1, which means I have to cut this into 5 pieces to know how far down it goes for 1. And so 3 cut into 5 pieces is 3 divided by 5. So that's what division's for. And so the line must be starting at 3 and going down 3/5 for every x across. Right. Cool. But you can also make lines from just any point. Something like that. No, I don't want 8. 9. Yeah, let's do that. If I have a random line with a couple of random points on it, it is technically possible to create the equation of a line based on these 2 points. I don't know if this is something that they've explicitly shown you how to do, but I just wanted to talk about it because it is relevant in data analytics as well. So you could, if you wanted to, extend the line back to here and figure out where it crosses the y-axis, but you don't technically need to. All you needed is this description that helps you figure out what the coordinates of any point is anywhere based on where you are. So this is one of my favorite things to do. When I'm at the point x equals 2, the answer is y equals 3. So I'm going to say that I'm going to start at the answer 3. And then if I go any distance away from 3, that's going to be my distance, then that distance times the slope will be how far up you go. That's how these lines work. So it's going to be whatever the slope is times how far from 3 you go. How far from 3. And so if I'm at a particular point x, how far from 3 is x minus 3? Because x minus 3 is the distance between x and 3. Because if this is 3 here, and that's x there, then this distance is the whole thing minus the 3. So we've got equals 3 plus the slope times x minus 3. And the slope I can figure out from this bit here. I know it's gone across 2, and it's gone up 6. And so I want to divide the 6 by the 2 to figure out how far it's gone across for 1, up for 1 across. And so, oh, everything's 3s. That's not what I was expecting. Sorry, everybody. And so I get 3 plus 3 times x minus 3. It's a coincidence. I did not expect that to happen at all. Sorry about that. And so this is a perfectly good equation. I could do more algebra to turn it into a more traditional kind of equation if I wanted, but that's a perfectly good equation for a line if I want. And in some senses, this is more useful than other ones because it tells me how far I am compared to this point as opposed to this one. Okay. Thoughts, questions? All good, okay. If that changes at any moment, let me know. Right. So then, this is great. It's a lovely, gentle introduction. And then all of a sudden, in this course, there's like 7 or 8 different kinds of functions, all with different kinds of formulas, and every formula from the experience of those who have walked this path before us, every formula has its own interpretation for what shape the graph is going to be. And the only ones that are straight lines are these ones, which can be written, if you want, as something times something plus x, like that. Sorry, something times x plus something. But there are lots and lots of others. And one of the ones that is the most complicated, well, it's the second most least complicated, but there's a lot of information about it, is quadratic functions. So in Latin, quadrat means square. And so quadratic means squarish. And when it says square, what it means is it has an x squared in it. So a quadratic function has an x squared, and all quadratic functions are the same shape. Like that. And so it'll be something x squared plus something x plus something. That's what they'll look like. And all of them will be the same shape, either this way or this way. And already when I look at this, it has more stuff about it than a straight line graph has. A straight line graph is the same everywhere. Straight line graph is identical at every location on the line. No matter where you are, if you go forwards one, you'll go up the same amount. If you go backwards one, you'll go down that amount. The only distinguishing feature of it, like if I didn't know where the coordinate axes were, then I wouldn't be able to tell hardly anything other than the slope. But I can, if you've got coordinate axes, tell where it meets the axes. A quadratic function has at least this point here, where it stops coming down and starts going up. And that most people call the vertex or the turning point. And it's not the same slope everywhere. It's really quite gentle just here, and it's very steep over here. And the further away from the vertex you go, the steeper it gets. That's quadratic functions. Whereas linear functions, always the same steepness everywhere. But quadratic functions have a different steepness everywhere. Every point has its own steepness that's slightly different. And the further away you are from here, the steeper it gets. It's never perfectly vertical, no matter how it looks on a picture. It's always just at least a little bit sloped one way or the other. Okay, so that's a quadratic function. And if you draw it on a graph, then there's all these different options for what could happen about how it meets the axes. Now, every quadratic function has to meet the y-axis somewhere. So even if it's way over here, you may have to go way up here and figure out where it crosses the y-axis, but it'll happen somewhere. But the main problem is, what about where it meets the x-axis? It could be like that and not meet the x-axis at all, or like that and not meet the x-axis at all. Or it could be like this and just meet it in exactly one point. Or it could be like this and just meet it in exactly one point. Or it could meet it in 2 points. And those 2 points could be very far apart or very close together. And they can be narrow or wider. But suddenly, by being curved, there's all these different options for what could happen. Whereas with a line meets the y-axis once, it meets the x-axis once. That's all there is to it. Quadratic functions are only just a little bit more complicated than linear functions. One extra piece of the formula, but suddenly, whoa, all this stuff happens. How do people feel about quadratics? Like in the room and the Zoom. Cool. I'm talking about this because I had a request. So at the end of quadratics, I'm going to stop and ask you for requests for things to talk about. Okay. I ideally love quadratic functions. I think they're really cool. And there's a lot of stuff about them. And here's where it gets really interesting. Different ways of writing this formula tell you different information about what the function is doing. So with a straight line, that wasn't so obvious. It is possible to write this function in different ways and get new information about what the function is doing. And I already showed you one. If I write it like this, then this tells you how it moves relative to x equals 3, as opposed to how it moves relative to x equals 0. And that's just one aspect of that. But for quadratic equations, it's really a lot. So I'm just going to talk through all those things because I found in the lecture notes, there's like a half-page list of everything you could know about quadratic functions. And it looks to me like it would have taken about 30 seconds in one of the lecture videos for them to say them all. And like, wow. So most people meet quadratic functions when they're 15 at school for the first time. I mean, it's a little like meeting fractions for the first time when you're 7 years old. If you don't get it at the time, everyone assumes you know it from that point forward and never explains it again. So that's why I just wanted to talk about this. So, all right. So we have information about this thing. We want a vertex. We want x-intercepts. And we want a y-intercept. They're the main pieces of information about a quadratic function. And we also have the orientation, which way up it is, whether it's this way or this way. Feel free to go if you need to go somewhere. Okay, so, and different things about the formula tell you different information, tell you these things in more or less useful ways. Okay, so there are things to hold on to which are always true for any function whatsoever. For any function, the y-intercept happens when x is 0. That is true for any function ever. Because all the points on the y-axis have coordinate x equals 0 because they line up with 0 on the x-axis. So they all have the x-coordinate being 0. So if you want to know what this point is, its x-coordinate must be 0, so you sub x equals 0 into the formula because that's how you find the graph. The y-coordinate is calculated from the x-coordinate using the formula. Okay, so that's always true. No matter how we write the function, if you want to find the y-intercept, you can always put x equals 0 in and get the answer. And the x-intercept happens when y is 0, by the same reasoning. On the x-axis, that lines up with y, with 0 on the y-axis, and so I need to make the y-intercept equal to 0, or if you like, f of x has to be 0, if you like. Not that y, it's just that when you're on the graph, y is equal to f of x for the points on this graph. Now, this is where it gets hard, because it's quite difficult for many of these to solve the equation of f of x equals 0. But these are always the truth, always, for any function. Okay, so writing the equation in different ways will make it easier or harder to do some of these things. This always is not that hard. This one is easier or harder if the function is written a different way. Okay, right. And that's pretty much the deal. We'll deal with that. So, for example, if I had f of x was equal to 3x squared plus 9x minus 8, then the y-intercept would happen when x is equal to 0. So I would go 0 for x, and I would get 0 plus 0 minus 8. And you'll notice it turned out to be this number, because those are both 0. Same as the way a line works, actually. The number is not attached to the x, has to be the y-intercept. And the x-intercept, 3x squared plus 9x minus 8 equals 0. And I have to figure out which x's make that come out to 0, and that is not nearly so easy. What? Yeah. But if I had an equation that was written this way, then my y-intercept would be that, which would be 5 times minus 8 times 1, which is minus 40. Wow, it's a long way down. And my x-intercept would be when this is equal to 0. And that's a lot easier, because the only way to make 0 come out when you multiply numbers together is for one of those numbers to be 0. You can't multiply numbers that aren't 0 together and get 0 as the answer. So you have to put one of these being 0. So 5 can't be 0 because it's 5, or this is 0 or this is 0. So x equals 8 or x equals minus 1. Because I added 8 to both sides of this and added minus 1 to both parts of this. And so I get two answers that both, no matter which one I put into here, will make the answer 0. If I put the 8 in here, I'll get 5 times 8 minus 8, which is 0 times whatever this works out to be. And if I put the minus 1 in here, I'll get minus 1 plus 1 is 0 times this, which is 0. And so if you can write it this way, then you have a chance of finding out what the x-intercept is. And that idea of rewriting something as the product of a whole lot of things, of many things multiplied together, and making it equal to 0 so that each of the parts, one of them has to be 0, that's a repeated idea in mathematics all the time. And it doesn't matter whether you've got a quadratic formula, a quadratic equation or not, if you can write it that way, then you can make the decision of what the zeros are. In the USA, they call this the Null Factor Law. Yeah. So this format is called the factorized or factored form. This is what's traditional in Britain and Australia, and factored is a much more American way of saying it, but it's quite common in Australia as well. The Americans, if they wrote this, they put a Z there, but they don't write factored. And the reason it's called factorized is because the word factor means thing that is multiplied to produce the answer. And so I have written it as things that are multiplied. That's why it's called factorized. And the act of factorizing a quadratic equation can be quite difficult. And so if I could rewrite this somehow to look like this, then I'd be onto a winner for figuring out the x-intercept. But there are other ways to rewrite it as well. If I'm very lucky, I'm going to do one more example of a different format entirely. This one. This does not look at all like the other ones. I can make it look like the other ones if I want, but I'm not going to. The y-intercept was the same as always, sub in x equals 0. I get minus 2 times 7 squared plus 6. Oh man, I've made it hard for myself. Well, 2 times 50 would be 100, so 2 times 48 would be 98. Minus 92. And the x-intercept, always the same, beginning. I need this answer to come out to 0. Now, I'm going to ignore everything I know about quadratic functions. I don't have to factorize it to solve this problem. I can notice that there's only one x written on the page here. And if I can peel off the things that have been done to the x, then I can get the x out. So I can subtract the 6. And I can divide by the -2, and I can square root. I didn't give myself enough space. And technically, I'm allowed to have positive and negative numbers, so I'll have to put a plus or minus. And so therefore, my x is coming out to -7 plus or minus √3. And that means that I could actually figure out what the answers are by getting my calculator and doing -7 plus square root of 3 and -7 minus the square root of 3 separately. So this actually wasn't that bad. I was able to use ordinary algebra moves to solve the problem. So this format is called vertex form. And the reason it's called vertex form is because the vertex happens when this is 0, which is really cool. And that's what I like. So, yeah. And so the different forms tell you different things. So here's the problem. Like, people have known about this for thousands of years. There are shortcuts to getting to the right information. So if your function is already written like this, number x squared plus number x plus number, then there's a formula for figuring out what the x-intercepts are, and it's called the quadratic formula. If you can rewrite your function to look like your equation to look like this, then the answers for x will be -b plus or minus b squared minus 4ac all divided by 2a. And I would recommend, so going back to that first problem that I had, my a is 3, my b is 9, and my c is -8. And so my x will be -9 plus or minus the square root of 3 squared minus 4 times 3 times -8, all divided by 2 times 3. $12 times 8, 96. I don't want to go any further than this. I've had enough of that. And so you would go to a calculator and you'd stick in -9 plus √105 and then divide by 6. And then you'd stick in with a minus instead and you get 2 different answers. But sometimes, if this bit works out to be a 0, you'll get only one answer because plus or minus 0 doesn't make a difference whether it's plus or minus. And sometimes, if you're particularly unlucky, you will get a negative number under this square root sign, which you can't actually do, and there's no answers at all. Last piece of information that's useful. If it does have 2 places where it crosses the x-axis, say it crosses here at 3 and here at 10, or let's say 17, then the vertex happens exactly halfway between, always. It's perfectly symmetrical, and so from 3 to 17 would be 14, and so we go up 7, so this would be 10 in the middle, which you can do by adding them together and dividing by 2 if you want. It's the average. And that's really useful information if you're trying to figure out, if you've got something that is quadratic and you know where it crosses the x-axis, then you know the maximum is guaranteed to be halfway between them and you don't have to do any other work. You can just say that's where it is. And it's useful information. Yeah. So it's useful also to know that when you do the quadratic formula, you have this -b plus or minus. So halfway between, because it's -b plus a bit and -b minus a bit, halfway between will be at the minus b. And so your vertex is guaranteed to be, so if you've got minus b plus or minus the square root of b squared minus 4ac, if I divide by 2a each piece separately, which you're allowed to do, then we're saying that the x-intercepts are minus b on 2a plus a bit and minus b on 2a minus a bit. So this must be in the middle. And so you've got that the vertex happens when x equals minus b on 2a, which is really cool. And it will even happen then, even if it doesn't cross the x-axis. So the reasoning works when you use when it has x-intercepts, but even if it doesn't, it's still at that place. And so if I had a function like that, and I wanted to know what the vertex is, then I could say the x-intercept, the x-coordinate of the vertex would be, that's A and that's B, would be minus B on 2 times A, which is 18 on 14, which is 9 on 7. And the y coordinate at that x point would happen when you sub the x point in. So I take the 9 on 7 that I've got for the vertex and I put it in these coordinates, and it should tell me what the y coordinate is. And that's not going to be pretty. That's what calculators are for. Do not like it. It's going to have sevenths in it. That was my fault for myself. I shouldn't have done that. Yeah, no, let's do it. 7 times 81 on 7 squared minus 18 times 9 on 7 plus 9. Oh, yay! That's fun. Look, that 7 cancels with one of the ones in the square. And the 18 is 2 times 9. Which is 81 on 7. Oh. And so I've got minus 1 81 on 7 minus 2 81 on 7s is minus 1 81 on 7s. Oh, that's nicer. What's 7 times 9? 63. So 9 is 63 on 7. And so that would be 7 would get me to 70, and then 10 would get me to 80. So I'm at 17 and 18. Cool. Wow. I think that's a complete coincidence that it came out to have some of the numbers that were in the formula before. Other than the 7, that's not surprising because you had to divide by it. I like practicing arithmetic. It makes me better at it. Yeah. All right, that's probably quite enough of quadratic functions, unless someone wants to ask or say something. Cool. All right. Your question. So while we're on, I'm just going to say there are other functions. I'm not going to talk about them unless you ask at some point, but I'm just going to make sure they're there. You've got exponential. You've got polynomial. You've got logarithms. You've got rational. They're all different kinds of functions on top of the linear and quadratic that you already have. And every one of them will have different ways of making decisions based on the way the formula is written about what those functions look like. And one of the points of this course is so that when you go on into the rest of your lives with finance and economics and just life, you can look at an equation, the formula for a function, and go, oh, I recognize that. I know what shape that's going to be. I have expectations about what that shape is like. And I know the algebra rules that go with it. And so you're going to have things like the shape of the graph, and the algebra rules that go with it. That is not how you spell algebra. So these are the things you want to know about any one of those functions. And how the shape of the graph is related to the way the function is written. And it may be that you have to rewrite the function in order to figure out how what the shape is. But that's just a point I wanted to make before I move on, that all of those considerations for the lines and the straight and the quadratics are good things to do. So if I were writing myself a summary sheet of those things, I would say this type of function, this is what the graph looks like, this is how the numbers in the formula relate to the graph, and this is the algebra rules that I'm allowed to use for it. Okay. Well, the other thing that we did, I wasn't there, that you did with the functions was inverse functions. So this goes all the way back to this drawing here. Functions, you get a number in, some sort of formula or process, it doesn't matter whether it's a formula or not, and it spits a number out. Okay. And the function is the name, the word for the process that gets from here to here. And it's usually a formula, but it doesn't have to be. What if my description of the way to do this action is to do the opposite of a different action? That's what an inverse function is. And so if I had something that 0 went in and the function produced the answer 3, and 1 went in and the function produced the answer 7, and 2 went in and the function produced the answer 11, and so on. What if I created a new function that when I put the input 3 in, it spat out the answer 0. And when I put the input 7 in, it spat out the answer 1. And when I put the input 11 in, it spat out the answer 2. The exact function that however the formula is, I don't care whether it has a formula, but my description for how to do this function is to say, oh, we take a number and we go and look at the outputs for my old function and I find the matching input and that's the answer. That's the description. I'm going to be really facetious about this. I'm going to write that down. So I have my new function. So we take input x, and then you go and find x in the outputs of f of x and write down the matching input. Not f of x, just f. That is the description of how to do it. We've got an input x, go find x in the output of f and write down the matching input from f. That's what the inverse function is. And so this function is f inverse of x is do this process. Right, and this -1 is an annoying layover from when they thought all functions were multiplication, but they're not, right? This function isn't just multiplication, it's multiplication and addition. But when they first defined function notation, they thought everything was multiplication. And so, unfortunately, that's where we are. Sorry, people. But what actually comes from the other thing that when you did a function twice, like you did it first and then you did the function again on the output, they used to call that f squared. And so like do f twice. And so if you do f backwards once, then it's f minus 1. That's what that means. So as f inverse of x. And then this thing means do f backwards because of the minus once. As opposed to doing it backwards twice, which is something else you could do. All right. Cool, 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 cool. So here's the example that you had. Photos. Suppose f is a one-to-one function. It takes these values, x and f of x, 2, 4, 7, 10, 12, 4, 7, 10, 12, 13. Okay. So if I wanted, I could draw a graph of this function. I could go to x equals 2 and go up 4 and draw a dot there. I could go to x equals 4 and go up 7 and draw a dot there. Go to x equals 7 and draw go up 10 and draw a dot there. Go to x equals 10 and go up 12 and draw a dot there. And go to x equals 12 and go up 13 and draw a dot there. My guess is that if the pattern continues, if x was 13, the answer would be something. Oh no, that doesn't work. Damn it. I could maybe go backwards. Nope, no idea. We don't have enough information to figure out what this function is doing. We can make a guess, but we don't have enough information. So what I do know, just for example, I can continue from this. I know that f of 2 is 4, for example. That's what this is telling me. And I know that f of 7 is 10. I know that f of 12 is 13. They're just some things. Technically, I know f of 4 is 7 and f of 10 is 12 and so on like that. Let's put them all in. I don't need to write this all down to do the problem, but I just wanted to point it out. So the inverse function, all right, so it asks for what is f inverse of 12? That's what it asks for. So what this means is, so I don't need this information, but it's what I'm thinking about. F inverse of 12 is the number 12. Go and look in the outputs for the number 12. There it is. And find the matching input. It's 10. So f inverse of 12 is 10. That's how to do an inverse function. I take the number that I've got, f inverse of 12. I take the number 12 and I go look in the outputs, and then I find the matching input that would have produced 12, and that's the answer. How do you feel about that? So I'm going to ask someone, what is f inverse of 7? Good. I'm going to ask a trick question. What is f inverse of 2? We don't know, because 2 doesn't appear in the outputs, so we can't do our function. And just wanted to put that out there, that unless you have a formula, you might not have a chance of knowing what the inverse is. So, cool, okay. I have something. Have a look at what's on this page and tell me if someone had a question about this. Oh, are we going to ask something? If someone had a question about what was written here, what might that question be? I know it's a weird thing for me to ask, but
what do you mean?
I just mean you might not have a question, but someone might. And this video is going to be watched by other people. So you might be able to think of something that someone might ask that they would want to know when they watch this video. Just wondering if you've thought of any of those things. If you can't, that's okay. But it's nice to be altruistic like that sometimes.
So if it wasn't one-to-one,
Mm-hmm.
you just wouldn't be able to solve what negative one is, because then you've got two values.
I'm going to just repeat that. If it wasn't one-to-one, okay, so you're telling me if it wasn't one-to-one, then you would expect there to be two answers here that were the same.
Or just that you're not going to tell because you don't actually have the
Yeah, you wouldn't be able to tell. This is a really good thing. Thank you for bringing it up. I hope someone would. I would have done it myself, but I really wanted one of you to do it. So one-to-one means that every input produces a different output. And you're saying if it wasn't one-to-one, then you would actually have no way of telling whether F inverse of 12 meant anything, because there might have been some other number that produced the answer 12. And so you wouldn't know which X it was, which input it was that made 12, so you wouldn't be able to decide what F inverse of 12 was. Is that what you were saying?
Yeah.
Yeah. So what that means is that if it's not one-to-one, then the statement F inverse, that function, isn't a function. Like you can't call it a function because there are some inputs for this that you can't find an output for because you've got multiple choices for what the answer could be. And that's why we're so careful to define functions as things that only produce one output for every input. Yeah. So we could imagine that there's the 2, 4, 7, 10, 12, and then maybe, we don't know for sure, but maybe there's like, when we put in 13, the answer is 10 again. And in which case, when we try and do F inverse of 10, we go and find 10 in the outputs, and there's two possible answers. Which one? I don't know. There is no answer because there is not one. And so F inverse doesn't exist. If I restrict myself to just these, then F inverse is fine. But if I restrict if I'm allowed to use any possible output, then I can't do it. And so that means that's the idea. For F inverse to exist, you need F to be one-to-one. Cool. And they'll be very careful in their writing of that test to say the word one-to-one so that they covered themselves legally. Because if they didn't say one-to-one, a perfectly valid answer would be, I don't know if it's one-to-one, the inverse might not even exist. Sucks to suck. So yeah. So if they did that in the exam, as a marker, I would be like, you smart ass, but also you're totally right. So if they don't say one-to-one and ask you for the inverse, you'll say, there is no inverse. It's not one-to-one. Yeah, cool. Okay. See, every question, even one that turns out, even one that you kick yourself and go, oh, that was simple afterwards, after the fact, has something extra to learn from. So, yeah. Any other thoughts or questions about inverse functions? Cool. One thing I will mention back here is that on this list, these two functions, they're inverses of each other. We normally define logarithms as the inverses of exponential functions. In the history of maths, logarithms were invented first, and exponentials came later. which was fascinating. But when they teach you exponentials first and then logarithms come after. It just tells you there's no real reason why we have to teach things in the order we do. Yeah, big fan of logarithms. Rational functions as inverses tend to also be rational functions again. Yeah. And quadratic functions in general don't have inverses because when you try and solve them, you get the plus or minus, so there's two answers. So in a technical sense, it's not a function trying to go backwards. But you can still say there's two answers. You just can't say it's a function. So, yeah. So there you go. I'm a big fan of inverse functions. Does anyone want to see me find the formula for an inverse function? Yeah? Is this something that you've been asked to do, something like this, and then find F inverse? Cool. So this is a rational function. A rational function has a polynomial on the top and a polynomial on the bottom, possibly just a number on the top. That's okay as well. Rational functions are, well, rational functions where the top and bottom are both linear are one-to-one functions. So that's okay. Yes, f of x is one-to-one. Okay. So, all right. So the inverse really does exist. Before we go into that, I just want to think about this rational function. It's not actually possible to calculate this rational function for every value of x. If x was minus a half, the denominator would be 0, and we wouldn't be able to actually calculate it because we'd have to divide by 0. So technically, this function doesn't have an answer when x is minus a half, which means that the inverse function is not going to be capable of producing the answer minus a half because minus a half doesn't produce any answers. Okay, so let me just talk this through. F inverse of x is going to be go and look up x in the output from f of x, from f, and then figure out what the input would have had to be to produce that answer x. That's what it is. And so I can't use x here because I'm using x as the output. And so I need to give it a different name. So I'm going to say, suppose f of y is equal to x. And then I'm going to figure out what the y is that produces that x. You could use any letter here that you want. It's tradition to use y for important reasons that will become clear later. So I've got 3 minus y over 2y plus 1 is equal to x. And then I have to figure out what the value of y is that produces this x. And so I'm going to have to unwrap this and figure out what y is equal to. So, so let's have a look at this. The most annoying thing about this is the fact that there's a y on both the top and the bottom. I'm going to remove that annoyance by removing this from the bottom. I'm going to multiply both parts of this by 2y plus 1, and now it will look like this. Actually, just for the purposes of people reading this sheet later, I'm going to remind them what the original line was so that on this page, because, you know, start with this, like, where did we come from? Okay. So now I'm here, and now the most annoying thing is that there's two y's and then on opposite sides of the equation. And this one is annoying because it's trapped inside these brackets with this x. So I would really like to combine all the y's together into one y written on the page. And to do that, I'm going to have to free this y from inside these brackets. So that's what I'm going to do. And multiply this x by both of these pieces because that's how the distributive law works. And now I'm going to try and move all the y's together to be on the same side. It occurs to me that if I move this over here, it'll be a minus, and then there'll be lots of minuses flying around. So I'm going to move this one over here instead. And I'll move that x out the way. So now at least all the y's are together on the same side. And I noticed that if I did the opposite of this move, I would be able to have only one y written on the page. And so I can factorize to get 2x plus 1 times y. It's the same. Oh, I did not expect that to happen at all. Sorry about that. And then I'll divide by this. And that's the answer, that's the y that would have been needed to produce the answer x. And so what that means is, I'll just talk this out, f inverse of x is the number that you would need to put in this position to produce this answer. And we've just discovered that that number is 3 minus x on 2x plus 1. And so coincidentally, the inverse of this function is the same function again, which is, I can tell you, is extremely rare. And I am thoroughly surprised. Yeah, very surprised. Did not expect that to happen at all. So if this had been, so if this 1 had been not a 1 but any other number, then we would have gotten a different formula. Because if it had been like a 4, then we would have had a 4x and we would have had a 3 minus 4x. Yeah, okay, cool. I love it when that stuff happens. I just want to be absolutely certain that I'm right. If I'm right, then when I do start with the number x and I do f, I'll get an answer. And then if I do f inverse on that answer, I should get back to the original x. Because that's how inverse functions should work. So just to check, if I do f inverse of f of x, it should be x. So let's see, 3 minus 2 plus 1, and then I put in that spot f of x. This should work out to be just the original x I thought of. I wouldn't recommend doing this all the time, but I just wanted to point it out. I notice that both top and bottom have a 2x minus 1 on the bottom of the bottom. So if I multiply the top of the fraction by 2x plus 1 and the bottom of the fraction by 2x plus 1, I should get 3 lots of 2x plus 1 minus 3 minus x and 2 lots of 3 minus x plus 2x plus 1. And then I can expand out the top and bottom, 6x plus 3 minus 3 plus x over 6 minus 2x plus 2x plus 1. And so they cancel and I'll have 7x on the top. And then they cancel and I'll have 7 on the bottom. And the answer is x. Checks out, does exactly what it's supposed to do. Ah, that's so cool. Correct. Okay. So if someone ever asks you, someone ever says not to find the inverse, but to verify that it really is the inverse, this is the sort of working you'll do. You'll sub the inverse, the original function into the inverse, or vice versa, and do calculations. And if it comes out to be just x all by itself, then it really is the inverse. Because sometimes you don't have the tools that you need to do this move, but this move might be a little easier to do. All right, questions, thoughts? Just time to chill. Cool. Important for me to stop every so often. Actually, I'm just going to have a drink. All right. Well, dealt with your question. Anyone else have something you want me to talk about? I can keep going. I can also stop.
Someone else got a question, but what about minimize version of the simplex tableau? We've done a lot of maximize.
Yeah.
I'm just curious on how you just think an example of it. Because how do you sort of swap the initial problem so it's swap it back at the end?
I'm going to pause the recording for a moment while I look up the notes to remind myself how that works, and then I'll find an example to do. And it might take me a moment to find a good example that will actually work. So just bear with me for a minute. All right, we've got a plan. We're going to find one that we know has a solution because we did it with the slack variables and subbing in vertices thing. I'm going to do it with the simplex algorithm instead. I love it. So I'm just going to write down the question. Not there. Not there. There. So we're going to minimize f of x1, x2 is x1 plus x2 subject to 3x1 plus 2x2 is greater than or equal to 12, and 4x1 plus x2 is less than or equal to 11, and x1 and x2 is greater than or equal to 0. All right. Where's my camera gone? Okay. And we'll use the simplex algorithm. So my understanding is that we have to put the slack variables in. And so we're going to make I would traditionally call them S1 and S2, but you're allowed, they'd probably call them X1, X4 and X5, X3 and X4. Yeah. And so we're going to have 3x1 plus 2x2 is greater than or equal to 12, and you'd normally transfer that into minus 3x1 minus 2x2 is less than or equal to minus 12, so that you can put the slack variables in and be positive. But am I right? I'm just bearing with me. Yeah. Yeah. Plus slack variable is equal to minus 12. Yep. Okay. Cool. 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 That's the first equation. And then the second one's already in the right format. And so we'll put a slack variable for this one. Yep. And then because we want to minimize, we're going to make a new function which is minus this one. So z equals the function we want to maximize. And so we're going to say that z is minus the old one. Pretty sure? If that's the advice you've been given?
Yeah, I think so. Yeah.
Give it a go. And so then we'll rearrange that and we'll get x1 plus x2 plus z is 0. Yep. Cool. Okay. And so then we set up our tableau. And so we have this, we've got x1 and x2 and x3 and x4 and z and the answers. And that's how we make the tableau. That's right? So x1 is 4 of them and 1 of them Nope, sorry, wrong one. There and there, there. So I've got -3 of these, -2 of those, and 1 of these, and no x4s, and no z's is -12. And this one is 4 x1s and 1 x2, and no x3s, and 1 x4 is, and no z's is 11. And we've got 1 x2, 1 and 1 x2, and no x3s and no x4s, and 1 z is 0. Yep. Okay. I'm distressed because aren't you supposed to look for negative numbers? I don't have any. Like, isn't that what you're supposed to look for here? Like the most negative?
Yeah.
Give me a moment, just bear with me. Yeah, so they didn't use the simplex algorithm for this one. They used the find all the vertices and sub them in thing. So have I misunderstood? Yep. Oh, chat. Yes, the negative of the objective function. The objective function was this thing. Well, thank you. The objective function is this one thing, and we've done the negative of that here. So maybe I'm misunderstanding the simplex algorithm. And that's why you wanted to talk about this, because you're going like, what, maybe? So we set up the simplex tableau. I mean, the simplex tableau seems to suggest that we've found the optimal solution, but it's not true, right? Because the optimal solution we've been told is 5, according to the answers to that problem. Bear with me.
What about you put z to the other side? So you put, when you did z to there,
Oh, yes, yes. You need the z, no?
No, because that would still sort of means that even if the equation's wrong. Because if you do negative x1 take x2 take z equals 0, just that doesn't work.
Yeah.
No matter what your
Sure it did.
z is, you've got
So we need to set it up so there is a negative. No, I like it.
So I think somewhere you've gone wrong with your objective.
Yeah, I reckon you're right, that instead of arranging it the way we've done, we should arrange it this way and go 0 is equal to -x1 minus x2 minus z.
Doesn't that happen equal 0? 3.
Oh, well, just they're not technically, they don't have to be negative. They could be 0, and -0 is 0.
So then we make
Yep, but that's okay. That's just an option. That's one of the options, but we want to find the other options that are better. So I think that if you want to maximize your function, you need to arrange it in such a way that there are some negatives. Like that. Yeah. And it's okay for this to be a -1. I know in the traditional Tableau it's a 1, but we need to make sure there are some negatives or we're not going to be able to do the problem at all. Could be wrong, but I'm going to give it a go. So you're supposed to choose the most negative one of these things, and they're all equally negative. And so does it matter which one? Did they tell us how to decide between the most negative ones? I reckon it doesn't matter. We'll just pick one. So we want to pick one that's not all zeros above, so that we can make a decision of which row to pivot on. So we're going to get the most negative one, and we'll just pick a negative one since they're the same. So I reckon when we have a most negative thing, it is technically possible for them to all be equally sized. So I don't think it matters which one. So we're just going to pick one like that. And then we're going to go, what's the next thing you do? You do the divide that by the thing. So -3 divided by, and you divide by the negative number or by the positive version? By the positive version?
Yeah, so to go back to the, yeah, so it has to be row 2. Because row 1.
No, but just a second. The thing we're dividing by is this negative number?
No, so it's the answer divided by each number individually in the row. So you do -12 divided by -3.
Oh, this divided by that?
Yep.
Yep.
Whichever one's the smallest, so you can.
So -12 divided by -3 is 4.
Yep.
And then separately, 11 divided by 4 is whatever that is, 2 and a bit. Yep. Okay, so you go smallest non-negative one is this one. And so that's the pivot row, is pivot row number 2. Cool, gotcha, thank you. And so we want to put a pivot there. That's the story. Yep, cool. It's always in the last week. And so that's usually the week that I'm out doing other seminars. And so I miss out being in the drop-in center and talking to people about this. And in last year, they cut it from the exam. So I didn't talk about it. And so now you go put a 1 here. So we go this divided by this. So we're going to go row 2 is row 2 divided by 4. And we're going to get 1, 1/4, 0, 1/4, 0, whatever 11 quarters is. And this is still -3, 2, 1, 0, 0, -12. And then we're gonna, oh, so you need that to be positive so that when you add it on here, it gets bigger. Oh, so cool. Okay, so clever. And then we're gonna go row 1 is row 2 plus 3 of row 1 plus 3 of row 2. And row 3 is row 3 plus row 2. So we're gonna get this plus, so we didn't change the middle row. And then the top row becomes this plus 3 of that, which is 0. This plus 3 of that. 2 is 8/4. -8/4 plus 1 plus 3/4 is -5/4. This plus 3 of that is still 1. This plus 3 of that is 3/4. This plus 3 of that is 0. And this plus 3 of that is, oh my God, 48/4. -48/4 plus 33/4 would be -15/4. And then this would be 0, -3/4, 0 plus 1/4, -1, 11/4. And so then we do it again. We find the most negative number, which is this one. Yep. And then we're stuffed, right? I think you can, but I reckon that the thing to do is not to just minus it. I reckon we're going to have to do some other thing. There's a whole different approach to turning it into something that we can minimize, which I don't think they taught you. Yeah. He does? That's all good. You can have a look at that. I'm interested to know what he said. What did he do? Do you know what his first move was? I think we're going to get kicked out of this room in a minute, but I'm very interested to see what that is. But just to pass on to whoever's watching this video, apparently it is in week 10 videos this year in 2022. Don't know what it's going to be like in the future, but it must be somewhere. Yeah, very interested to find out, actually, because I feel like we're doing something wrong. Yeah, so you're not allowed to use this argument. Yeah. Well, thank you, everyone. Good luck with your exam. Maths Learning Centre is open during the exam period, so check us out, and I'll see you soon.